Okay, before we continue with a review of the different ways of measuring the distances to objects in our universe, just want to do a review of what we've done so far. So we've got spectroscopic parallax up there at the top, Cepheid variables, Tully-Fisher relationship, and then in just a few moments we're going to do the standard candle and then the Hubble's law. So with spectroscopic parallax, notice that you're going to be using an HR diagram that has the temperature of a main sequence star versus the actual brightness of the main sequence star. So that what you're going to do is you first get the temperature of the star, you're going to bounce it off the curve, and then you're going to figure out the actual brightness, and then you're going to use photometry in order to figure out the distance to the object. With the Cepheid variables, you're going to use a chart, but this time the chart is going to be the period. So this is not the temperature, because you notice it's got hooks on the T. So this is the period. It's the time it's going to take for the Cepheid variable to get bright, and then to get dim, and then to return back to its original brightness. But you're still going to bounce it off the curve, and you're going to get the L, and then you're going to use photometry to figure out the distance. Okay, with the Tully-Fisher relationship, you're going to use a graph, but this time it's the rotational speed of a galaxy. Bounce it off the curve, get the actual brightness, use photometry to figure out the distance to the object. Now, let's do the standard candle. So with a standard candle, you have a binary star system in which you've got a regular star, and then you've got a white dwarf, which is dead. And they're both in orbit around each other. But because the white dwarf has gravity, it can still pull hydrogen and helium off of this normal star. And then if the white dwarf gets big enough, it will collapse, and then you'll have a supernova. And the actual brightness of this supernova has been calculated. So that all you've got to do is you look for one of these supernovas, you measure its apparent brightness, and then using photometry and the actual brightness L, you can figure out the distance r to it. So you notice that this one does not have a graph that goes with it. Okay, so here's a sample question that shows you how you would go about using this technique. And now we want to talk about our final method of measuring distances in the universe, and this is going to be using Hubble's law. And you'll notice that it has a graph that goes with it. But this one is kind of unusual. It doesn't have luminosity over here. It's got the speed at which a particular galaxy is moving away from us because of the expansion of space and time. And then over here is the distance. Now this time you're not going to be bouncing it off the curve. What you're going to be doing is using the slope of this curve. So the slope of this curve turns out to be Hubble's constant. And so there's going to be two equations that you're going to use in order to figure out the distance to a galaxy using Hubble's law. So the first one is going to be that the speed at which a galaxy is moving away from us is going to be the speed of light multiplied by the change in the wavelength of the light divided by the original wavelength of the light. So the original wavelength of the light is going to be what was the wavelength of the light if you were just looking at it in the laboratory, and the source of the light is not moving. On the other hand, if the light is moving, it's coming from a galaxy that's moving away from us, its spectrum is going to be shifted. And so you're going to subtract those two numbers, and so that's the change in the wavelength. You're going to multiply by 300,000 because that's the speed of light in kilometers per second. And then divide by the original wavelength, so now you've got the speed of recession. And then to find the distance r to it, all you got to do is take this result and then divide by 22, because 22 is considered to be the current value for Hubble's constant. And then that's going to give you the distance in mega light years, millions of light years away from Earth. So here is a sample question. You have to be able to do this on the exam. And then here's a comparison of the various ways of measuring the distance to an object. Okay, and then we also, it's important for you to know what's the point. So why is Hubble's constant h sub 0 so very important? So number one, it determines distances. So we just got finished with that. The distance to a galaxy is going to be the speed of the galaxy divided by Hubble's constant. So I could ask you a question on the exam like this. It's a conceptual question where I say if h is actually bigger than what we think it is, or I could say if h gets smaller, what would be the consequence for the distance to a galaxy? Would that galaxy be closer to us, or would it be further away? Okay, the second one is that Hubble's constant determines the age of the universe. You're not responsible for knowing the derivation, but you should know that the age of the universe is equal to 1 divided by h sub 0. So that if we know the value of h sub 0, we can figure out the age of the universe. And again, I could ask you a conceptual question in which if I could say if h sub 0 is actually bigger, what effect would that have on the age of the universe? Okay, then we also have Hubble's constant determines the expansion rate of the universe. So you're not responsible for any derivations, but you notice that the expansion rate is directly proportional to h sub 0. So again, I could ask you a conceptual question about if h sub 0 gets bigger, what effect would that have on the universe? And then, lastly, we've got this one, that Hubble's constant determines the amount of mass and energy density the universe would need in order to stop its expansion. So the universe is expanding, and if there was enough mass in the universe, it would cause the universe to stop expanding. And that critical amount of mass and energy depends on the value of Hubble's constant. Okay, so again, a conceptual question. I could say if h sub 0 is bigger, then what would that mean about the amount of mass that the universe would need in order to stop its expansion? So these would all be conceptual type questions. Okay, let's take a break, and when we come back, we're going to talk about fundamental particles in the universe.